Hello and welcome to section 4.1b, Radians and Degrees. And in this section we're going to take this a little bit further. We're going to have some formulas that you're going to need to know. And so what we're going to start talking about is what a radius of a circle is. So here is my radius. It goes from the center over. And my arc central angle is an angle that actually goes to the center of the circle. This is a little bit off, but we'll call that theta. Theta will always be measured in radians, but if it's measured in degrees, then we need to remember that we multiply degrees times pi over 180 to equal radians. And so we'll need to remember that conversion that we practiced the other day. And so that's how we're going to get theta. And so then if that's how we find theta, we just multiply by the radius, and that will be how far, if I was walking from this point all the way around the circle to that point, how far I actually walked. So let's practice this a little bit. Let's put this into practice. We have this circle that has an angle of 240 degrees and a radius of 4 inches. So I have a radius of 4 and my angle in here is 240 degrees. And so we want to know how far is it if I was going to walk around my circle, how far would what is the length of that arc? And so in order to do this, I have to remember my formula. I have to remember that I'm going to change my theta is 240 degrees, but I need to change it from degrees to radians. So degrees to radians is degrees times pi over 180 will equal my radians. So I have 240 degrees. I will multiply that by pi over 180. And so that really gives me 240 pi over 180. Now if I reduce the 240 over 180 and kind of leave the pi out of this, I end up with 4 pi over 3. So that is the theta that I'm looking for. And so that's going to get plugged into my formula up here. They already told me that my radius is 4 inches. So I plug that into there. And so my arc length, S, will be 4 times 4 pi over 3. Well, multiplying that out, that gives me 16 pi over 3, which is approximately 16.76 inches. And so that's how far I would have to walk if I was walking from one start of my angle to the end of my angle. So let's try this again. In this one, we're talking about the minute hand of a clock is 11 centimeters long. How far does the tip of the minute hand move in 30 minutes? Well, in 30 minutes, the minute hand is going to go from, if it was at 12, it would go down to 6, straight down. And so if that's the case, then we are going to know that it's going to be half of the circle, which is 180 degrees. Or we could do 30 minutes out of 60, which would give me a half, and then we multiply that by 360, which would be 180 degrees, and then we can convert. Or we could have actually done this a little bit shorter and said, oh, well, I know once around the circle is 2 pi, which in radians, so if I multiply a half by 2 pi, I have pi radians. So I had already done my conversion. So there is the arc length, that is the angle. Pi is my angle in radians. So if I'm going to find my angle, if I'm going to find how far the minute hand moved, the tip of the minute hand moved, that's going to be arc length, which is going to be S times radius times pi. Well, that would mean that my radius is 11 and my pi times pi, so I get 11 pi is how far it's actually moving, and that would be centimeters. And we could multiply that out and find out exactly what it was. So now if it's 40 minutes, I'm going to do the same thing. I'm going to say 40 minutes over 60, which would be breaking down how much it is, which is 2/3 of the clock. And so then if I multiply that by 2 pi, that would tell me how many radians, because I'm using 2 pi as once around the clock, and so I want 2/3 of once around the clock, which then gives me 4 pi over 3 for how far the minute hand's going to move in 40 minutes. And so then to find my arc length, I'm going to say, oh, well, it's still 11 for my radius. This time I'm going to use 4 pi over 3, and I'm going to have 44 pi over 3 centimeters is the length that the clock actually moves. And you could find out the approximate length by calculating it out with your calculator. So then we have some formulas that go along with this, and we're going to find linear speed. Linear speed measures how fast a particle moves along the circular arc. So now this is how fast the thing is moving along and not just how far it is moving. And so basically what they say is that to get speed, it is going to be distance over time. And distance over time is s, the arc length, divided by t. And I'm actually going to write this out as theta times r over t. So that is my linear speed. You're probably going to use this one a little bit more. Very rarely do they say the arc length is this, and then you have how far it goes. So you're probably going to use theta times r over t most often. For angular speed, well, this is how fast the angle changes over time. And when it changes over time, this becomes theta, the angle, over time. So remember that all the angles must be measured in radians. And then if we combine these two formulas up here, we could say that, well, if you notice, we have theta over t right here taken care of for our linear speed times r. So then we could say, well, if we're ever given the angular speed, we can say w times r would give me also my linear speed. So these two formulas right here are the same thing. It's just completing that the theta over t is being replaced with the w sign. So sometimes they give you the angular speed. And so for my next one, when I have got this, I have a child spinning a rock at the end of a rope that's 2 feet long at 180 RPMs per minute. So I know that my radius is 2, and I know that I'm going to have an angular speed of 180 revolutions per minute. And so, well, a revolution, if I do this conversion, is, if I say revolutions, let's see, this is revolutions now, and in 1 minute, and so now this is kind of like chemistry class when you're doing the equation balancing. I have revolutions per minute. Well, 2 pi is 1 revolution. It is radians, is the radians per 1 revolution. So now my revolution units will cancel out. So now I'm in radians per minute. And so if I multiply this out, that would tell me that my angular speed for this is going to be 360 pi radians per minute. And so that is the W. So now if I remember that to find my linear speed, that was V either theta R over T, or we could replace theta over T with W times R. Well, we know W because this is theta over T. Remember, theta is the radians over time, and so then we can basically just say, oh, well, we know that this is 360 pi times a radius of 2. So this would turn into 360 pi times a radius of 2, which, because W is my angular speed. And so then if I multiply that all out, I have I get 720 pi, and that's feet per minute, which comes out to be approximately 2,262 feet per minute. And then if you did the conversion to miles per hour, you might want to do that. The conversion to miles per hour is that this is 25.7 miles in 1 hour. And so that's how fast the rock is coming out. And so usually when we want to do when we want to find out the speed of the rock, yeah, we could leave it in feet per minute, that's fine. But sometimes you want to go to miles per hour, and that's just still another conversion like we had up above. So then if we have a second hand of a clock is 10.2 centimeters long, find the linear speed of the second hand. So if we're going to do that, we're going to go ahead and say that the linear speed of this is, well, S is, is theta times r. That's what we're looking at. So for our linear speed, I got to remember what we're doing here. So linear speed, theta times r. And if we want to find out how fast the second hand is going, well, we know that we'll just do one revolution, which would be 2 pi once around, and then if our radius is 10.2, we can just multiply those together, which would say that, okay, well, we're going at an arc length, this is arc length here, an arc length of approximately 20.4 pi centimeters. So there's our arc length, and then we'd say, oh well, how long did it take us for that second hand to go once around? Well, using our arc length, we're going to divide this by time, and so we will get v equals 20 over 60, because that's 60 seconds to go around, and so it's approximately moving at 1.07 centimeters per second. And so that's how fast the thing is going. So our linear speed, remember, can be written as s over t or theta r over t. And so I could have done this all in one spot that we were looking for linear speed. We could have gone, oh, well, v equals theta r over t. Well, that would have been theta was 2 pi, r is 10.2, and how long did it take me to get around there? Well, that was 60, and by doing that, I can get to this thing too. So I just kind of did it in pieces, or you could just use that and just use the old formula that we had previously and plug it all in. And this concludes our notes for today. If you have any questions, please come to class prepared to ask them. Thank you very much.